In this video I will discuss about some tricks related to chemistry. So let us start. The first is hybridization in complex compounds. So orbital for hybridization are 3d, 4s, 4p and 4d. The trick here is that all ligands with carbon and nitrogen are strong field ligands, and those ligands which don't have this carbon and nitrogen are considered as weak field ligand. So note, 4d and 5d metals forms low spin, means pairing with both strong and weak field ligands. So this strong and weak field ligand is applicable only for 3d elements. So then we have this one, coordination number, type of hybridization and structure. So if the coordination number is 4, then the type of hybridization is sp3. The structure is tetrahedral. If the coordination number is 4, then type of hybridization is dsp2. So then shape is square planar. If the coordination number is 4, then type of hybridization is sp2d. Then the structure is square planar for copper complexes only. So then we have this coordination number is 5, then dsp3 hybridization, and structure is trigonal bipyramidal. So then we have this one, coordination number 5. If the type of hybridization is dsp3, then the structure may be square pyramidal. So then we have coordination number 6, sp3d2 outer complex. So then the structure is octahedral. Then we have coordination number 6, d2sp3. So this is called as inner orbital complex. The structure is octahedral. So then we will consider the magnetic moment. So this formula is spin only. Mu(s) is equal to root n plus 2. N is the number of unpaired electrons. For number of unpaired electrons, the magnetic moment. If the number of unpaired electrons is 1, then the magnetic moment is 1.7. If the number of unpaired electrons is 2, then the magnetic moment is 2.8. If the number of unpaired electrons is 3, then the magnetic moment is 3.9. If the number of unpaired electrons is 4, then the magnetic moment is 4.9. If the number of unpaired electrons is 5, then magnetic moment is near to 5.9. So let us consider the molecular orbital theory. So for electronic configuration up to 14 electrons or less than 14 electrons at that time, so this pi x, pi y orbitals, molecular orbitals, they come first. If it is more than 15 or 15 onwards, so then this z orbital, it comes first. So let us consider this one, up to 14 electrons or less than 14 electrons. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, sigma star 2pz. So then consider the electron configuration above 14 electrons, that is 15 and 15 onwards. So sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2py, pi 2px, pi star 2py, pi star 2py, pi star 2px, then sigma star 2pz. So then consider the bond order. So it is half of the number of bonding electrons minus number of anti-bonding electrons. So then consider the hydrogen bonding. Electrostatic force between hydrogen atom and electronegative atoms such as fluorine, oxygen and nitrogen are known as hydrogen bonding. So here we have two types. One is intermolecular hydrogen bonding. In between molecules increases boiling point and its water solubility. So intramolecular hydrogen bonding, in the same molecule, decreases boiling point and its water solubility. So then we have this bond order. So it is Nb minus Na divided by 2, as bond order is inversely proportional to bond length. Bond order is directly proportional to bond energy. So then we have this hybridization based on VSEPR theory, predicting the type of hybridization of central atom or shape of the molecule. The trick is sigma bonds plus lone pair is equal to 2, then the hybridization is sp. If it is 3, then sp2. If it is 4, then sp3. If it is 5, sp3d. If it is 6, then sp3d2. If it is 7, then it is sp3d3. So sp linear shape, the best standard example is BaCl2 or BeCl2. So then we have this sp2 trigonal planar. The standard molecule is BF3. sp3 tetrahedral, the standard molecule is CH4. sp3d trigonal bipyramidal, the best example is PCl5. sp3d2 octahedral, the best standard example is SF6. sp3d3, then it is pentagonal bipyramidal. So we need to consider the special cases like SF4. So its shape is seesaw shape. ClF3, its shape is T shape. BrF5, its shape is square pyramidal. So then we'll consider this one, sp3d3. So it is 7 plus 1. So this actual shape is pentagonal pyramidal or distorted octahedral. So we'll consider this one. So fluorine and chlorine, they are called as monovalent species. So this oxygen is called as divalent species. Nitrogen is called as trivalent species. So let us consider CH4 example. So in this case, the number of valence electrons on this carbon is 4. So this each hydrogen is attached to one single electron. So then the number of sigma bonds plus lone pairs is equal to 4, because only 4 sigma bonds are there. So for that reason the number is 4. So for that reason it is sp3, and the shape is a tetrahedral, tetrahedral shape. So then we'll consider this one, hydrogen bonding. Electrostatic force of attraction between hydrogen and high electronegative atoms such as fluorine, oxygen and nitrogen and chlorine. Only these number of atoms, so then only it is considered as hydrogen bonding. Nitrogen, oxygen, fluorine, chlorine. So these will accounts for hydrogen bonding. So we'll consider this one. If it is a odd electron, then fractional bond order. If it is a even electron, then it is integer bonding orbital, means a bond order, right? So we need to remember this one, that if it is a 10, then the bond order is 1. If it is a 14, then the bond order is 3. So we'll consider this one, right? So if it is a 14, then it is 3. If we go above, then it decreases. If it is go below, then also it decreases. So 8 electron 0, 9 electron 0.5, 10 electron 1, 11 electron 1.5, 12 electron 2, 13 electron 2.5, then 15 electron 2.5, 16 electron 2, 17 electron 1.5, 18 electron 1, 19 electron 0.5, 20 electron 0. So one exception is there, that is a C2 molecule. The bond order is 2. In this case both bonds are pi bonds. So we'll consider the bond order for polyatomic molecules. Bond order is number of bonds around the central metal atom divided by the number of atoms around the central atom. So we'll consider this one, SO4 2 minus, sulfur, and here 4 oxygens are there. So in this case the bond order is number of bonds around the central atom is 6 divided by number of atoms is 4. That time the bond order here in this case is 1.5. So IBr is a non-polar, it is a covalent compound, and remaining interhalogens are polar, right? So only IBr is a non-polar covalent compound, other elements are the polar one. To find paramagnetic or diamagnetic species, if it is even number of electrons, then it is diamagnetic. If it is a odd number of electrons, then it is paramagnetic. So two exceptions are there. They are 10 electron and 16 electron. So both are paramagnetic. So example H2, 2 electrons diamagnetic. Nitrogen, 15 electrons, it is paramagnetic. N2, 2 minus, 16 electron diamagnetic. So this is wrong, because so we know that 16 electron, then it is a paramagnetic. Then we will consider this one, bond order. Bond order is nothing but number of chemical bonds between a pair of atoms is known as bond order, Nb minus Na divided by 2. If bond order is negative or 0, then molecule does not exist. So we'll consider this one. If number of electrons is 1, then bond order is 0. If it is a 2, then bond order is 1. Right? So like that we'll consider this one. If it is a 4, then it is 0. If it is a 6, then it is 1. If it is 8, then it is 0. So like that it will increase. So 10 electron 1, 12 electrons 2, 14 electrons, the bond order is 3. Like that 16 electron 2, 18 electron 1 and 20 electrons, it is again 0. So this is all about hybridization and molecular orbital theory. So remaining things we will going to discuss in our next video.